Hello everyone, thank you for joining this tNavigator webinar hosted by Rockflow Dynamics. Today's presentation will be given by two of our geologists from Aberdeen, the Aberdeen team, Jordan and John. This is the third part of our current series. If you'd like to see last week's webinars, they are uploaded to our YouTube channel. In today's session, Jordan and John will take you through each step in a typical static model build in tNavigator, showcasing our integrated workflows and advanced functionality. Everyone who's on today's webinar has been automatically muted. If you want to ask a question, please type it into the chat box in the control panel on your screen, and we have some time at the end to answer the questions. If we don't have time to reply to your question live, we will email you back with the answer. And we are recording this session, and I'll upload that to our YouTube channel later today. Thank you very much for everyone who's joined, and I'll now hand over to John to begin the presentation.
Thanks, Joanne. So hi everyone. As Joanne mentioned, I'm one of the geologists based here in Aberdeen for Rockflow Dynamics. I'll be working alongside my colleague Jordan today, and we'll be looking at how we can show you sort of the transformative workflows that we have here in Geology Designer within tNavigator to help build up your static modeling solutions. So without further ado, I will jump into their slides. So you can see that, Jordan?
Not yet. I still have the webinar series up.
Yep, that's fine. It's moving now.
Oh, there we go. It's moving.
Perfect. So as Joanne mentioned, everyone's muted at the moment, but we can take some questions towards the end once we keep posting them within the chat. So tNavigator, obviously there's a lot of people joined here today. Some people may have used tNavigator already, and some people may have just been coming across it as of late. But essentially, it's one asset, one software. We are one integrated reservoir modeling software. So we can take, we can build up our static modeling solutions, and build up our dynamic models, run some uncertainty quantification for both our static and dynamic sides, integrate it with some surface network modeling, and do some full simulations towards the end and run our assisted history matching and forecasts. So we can do everything under one roof. And today we'll be focusing on the Geology Designer, where we build up our full static modeling solutions, taking in where we can bring in multiple types of data, doing some geophysical interpretation, whether it's our seismic picking for faults on our horizons, looking at our geological interpretation, doing some machine learning for outputting some missing well data, doing some well correlations for markers. We can build up our structural models and then populate our 3D grids with some continuous petrophysical data, and also our discrete fascies models. And we'll be showing a number of different algorithms we have available today within this session. And then finally, we'll be showing off the uncertainty analysis that we can capture here within Geology Designer, looking at also our outputting local multivariate, so we can see new iterations within with each case we run in our sort of our 3D space, but also looking at our AHM uncertainty engine, where we can see run the sensitivity analysis on a select amount of variables for each of our cases and see what has the greatest effect. So if you've not seen already, this is the home interface for tNavigator. This is where you can find all of our domains within one software. So obviously, looking at your Geology Designer at the top left, this is what we'll be looking at in today. This is where you can build up our full static modeling solutions. So taking in your data, building up your grid, before passing onto your reservoir engineer. So this is where we build up our geological models. Geology Designer to Model Designer is almost an identical interface. It's just got a different license from one to the other, so our geologists or our reservoir engineers don't step on one another's toes, and they can work together, create integrated workflows, and it promotes a lot of collaboration between departments. So there's no mass transport or export between different domains. We can simply create integrated workflows between each domain, and the data will be transferred seamlessly. I'm just going to turn off my camera as we've got some videos coming up and I don't want to create any lag, so I'm just going to turn this off. So looking at sort of the complex problem, a complex model. So For geological modelling, it has gotten more complex as the years go by, and with this in correlation has been the tools that we have to our disposal. So allowing us to capture these ever greater complexities within our subsurface. So far too often, models can get too complex and software doesn't always help. So what I mean by this, so outside of tNavigator, projects will be built up in multiple platforms. So including your static build, your dynamic model, looking at your well design, your assisted history matching, everything may be done in a separate platform. So whereas within tNavigator, this can be done under one roof, allowing collaboration amongst your subsurface and surface teams and minimizing the number of errors between the data transfers. Because our domains run on a parallel code, essentially allows seamless communication from one domain to the next. We can integrate workflows between our domains, allowing for uncertainties to be captured across the full board. So from the top left image, we can see this is an image from Ringrose and Bentley from the reservoir modeling book. And it exactly shows the benefit of working with these integrated workflows that we have here within tNavigator. So by taking on the sequential approach, your standard typical approach before going into tNav, you can just see how each project is done in an isolated manner. So meaning that the time required by the user to complete a project is extremely large. But in the other case, by abandoning these sort of default workflows, we can save an enormous amount of time on our project build, having the ability to move from one domain to the other in a parallel fashion and update our variables and models on the fly without any sort of harsh import or exports. We save a huge amount of time and accuracy. So tNavigator allows us to do this. And our simple to use workflows allow us to move seamlessly between one domain and the next. So essentially allowing us to answer any of our modeling questions. So as maybe you want to just create a simple 2D model, upscaling it from your outcrop analog data, or creating a full 3D field model, we have the tools available to do this. And essentially by having these integrated workflows where we can jump back and forth between domains, update variables on the fly, update our models, going into simulation from our static to simulation, it's a lot of advantages to doing it this way. To the next slide. So I'm just going to pass over to Jordan now to kick things off, looking at going into our sort of our geophysics and our fault analysis.
Perfect, thanks, John. So hi everyone. I'm just going to talk you through the first part of the webinar. So for those of you who don't know, tNavigator also has a full kind of seismic package where we can do seismic interpretation, we can create some attributes. We've also just released seismic inversion, as well as things like velocity modeling, depth conversion as well in the package. For the first part of the webinar, of course, we're working through to build a reservoir model, and normally this will start with seismic. So we're starting off by picking some seismic horizons, and also we're going to pick some seismic faults as well. So we have 2D and 3D seeded auto tracking. We also have kind of like nice undo buttons to run through it like this, but we're just using 3D auto tracking to kind of create this surface. So we build up our lattice first, create our surface for these seismic points, and then we can then push this all the way through to the actual surface creation as well. So this is just what we're doing here. So the surface has been created, and I'm just displaying a dip angle map on this as well. So with the dip angle map, we can see the displacement of the faults quite easily. It just allows us to pick out these kind of highs and lows and areas of displacement a lot easier than just on a plain kind of surface. And it's the same with the dip azimuth map. So we can just create this from the seismic horizon or the surface that we've created to visualize our faults. We can also create a coherence map as well. So this is just created through a seismic horizon where we can see the fault displacement really nicely, and we can start to filter out the lower data points so we can see where our faults are more clearly. And what I'm doing now is just overlaying the attribute creation and the surface that I created on top of each other. And this allows us to kind of combine the two data types, place them on top, and make sure that they are like QC'd correctly and make sure that they're in alignment with what we think. So yeah, again, this is just coherence, and you can see here it allows us to pick out the faults really nicely. So we have these kind of strong structural Y-shaped faults appearing in the 3D window, and we can then go through and actually use tNav to pick out these faults on seismic, I've just split my screen here. So we have it in 3D and 2D and our seismic window as well. And with tNav, the fault surface actually gets created as you pick your fault lines. So it just allows you to check the structure as you pick. You don't have to go back and rerun your fault and have a look at it and rerun and have a look at it. It will just automatically create this nice visual surface for you, so you can make sure that your data is following where you want it to be. So we're just creating our faults here, just picking out. On these we have undo buttons and we also have eraser buttons, which is super handy. We're now putting the fault that we created on top of the dip angle map, and we can see here that maybe our fault hasn't quite captured correctly the angle and the dip of the horizon itself. So if you're just seeing here, the dip angle is showing us that the fault actually extends a bit further. So I'm just using some interactive tools just now to push my fault out a little bit, extend it out, and make sure that it's matching up with the dip angle of my actual surface. So once I've created all my faults on seismic, I've just popped it through to my 3D window here, and we're just visualizing them all. So before we want to create a nice 3D model, we want to make sure that our faults are kind of error-free. We want all our sticks to be as planar as possible. These definitely will grid in the software, but if we want to go in and have a little QC and check the dip of our faults or the angle of our faults, we can do this here. So this is just a dip attribute that I've created, and we can see the areas of like yellow or a bit higher dip and the areas of like the blue and green are a bit lower dip. So again, I'm just going in, doing some manual editing, removing some twisted sticks maybe, adding some more in. And then what I'm going to do is rerun the dip, and you can see hopefully this orange part here will just turn to kind of a lighter color as we've deleted some of the sticks, and then we have less of the dip in our fault here. So this is just a really nice QC tool to check all your faults before you, it's kind of a pre-processing before you process it through to gridding. We're now going to remove some of the drag zones from our data. So you can see here I have some wrong-sided data on one side of my fault. I can then go in and use this little lasso tool to drag around here. And yes, when this data goes through to the gridding, if we don't want to get any drag zones, we can actually come in, remove some of the erroneous data, just like this, and just delete them. So we do have automated ways of doing it, like clear fault 5, 10, 15, 20 meters away from the fault, of course. But if you want to go in and get anything kind of manually, pick out exactly which data points you want to get rid of, we have the option for this too, which is quite nice. So yeah, I'm just creating it here, and now you can see I have this nice kind of clean area where my fault was. Just some more fault attributes here. You can see that I'm calculated dip, and you can also calculate displacement and also throw. So here we can see the nice kind of different displacement and throw profiles of our fault. We want to make sure that we have this kind of normalized throw profile where it's smaller at the side and kind of tapering out at the side and then getting larger in the middle. And we can actually go through and have a look at our data and see if there's anywhere that maybe this isn't matching, and we might want to go and have a second look at the data. So here you can see I have like really big displacement in the middle and then tapering out the edges. But in some of the areas where the line gets really small, it's just because that fault hasn't truncated through all the different horizons. So this allows you to just go quickly see, okay, which one of my zones and horizons is my fault cutting into and which ones aren't. So we can either extend it, or if we know that that's how our geology is, we can just leave it like that. We also have a really nice automated fault QC tool. This will let you know if we have any faults that maybe need to be truncated, any faults that have bent or twisted or inverted sticks. So sometimes if we get, kind of messy data over from seismic, we're gonna sometimes have twists or folds in our faults. And if you have, hundreds of faults, you don't want to go through and manually check them all. So this tool is really nice. It just gives you like little red dots if any of your sticks are kind of like off its axis a little bit. We can then remove those sticks and rerun it. This will also tell you if any faults need to be truncated. So if any of your faults are touching or crossing, it'll give you a little warning and it'll just say, okay, these faults are crossing, and it can automatically truncate them for you as well, which is really nice. We can then create this nice 3D model. You can see all our zone ID property here from our nice clean faults and also our nice clean horizons. We don't have any kind of drag with our faults here. We've got rid of the drag zones, made sure our faults are nice, our sticks are all nice, and then we've actually created the 3D model from that data there. Another thing is this layering. So we can see we have this proportional kind of layering here, but in Geology Designer, we actually have this really cool tool which allows you to use logs to create basically the best zonation and best layering for your model. So what this can do is it will calculate the optimum layering based on a log. So where you've got areas of a lot of heterogeneity, so like really interbedded sands or shales, it will actually give you more layers for your grid. And areas where it's more homogeneous, it will kind of save the layers and give you these kind of larger areas here. So you can see with some of our zones, we have these really small zones where we have lots of heterogeneity, lots of interbedded fascies, and then the areas where we have kind of less of these little lines, it just means that there's a kind of big bulk of sand or shale, something like this. So this is a really nice tool, kind of automated way of picking your proportion table. We also have an automated way of picking markers. So you can see here, I have this kind of high gamma ray shale base, and I'm just picking out a few of the markers. But if you've got obviously hundreds of wells, you maybe don't want to go through and do them all individually. We have this nice automated kind of log marker creation tool where you can put in a number of logs and say, okay, at this response, give me a marker. So we put in some training wells. So in this case for gamma, I've put in some training wells. I'm just going to hit apply, and we can see here it's actually captured it all across our wells. Of course, you can put in some kind of tolerance and advanced settings as well to customize it a little bit to what you want. But yeah, it just allows you to kind of create these markers for the rest of your data. I'm now just going in and having a cross plot with V-shale and permeability, and then it's colored in by porosity. This is a good way to check if two properties are suitable for things like co-kriging, if we want to kind of populate them against each other. But before we go into our kind of property modeling, I just wanted to show another nice feature of Geology Designer where we have this machine learning well log. So we have two options for machine learning well log prediction. We have supervised and unsupervised, and they both use random forest algorithm to populate it. So again, for this one, I'm just using a training well log. So I have one fascies log, but maybe we're missing it for the rest of our wells. We can actually go in, add some training well logs. So where I have high permeability and low V shale, give me, sands, and then the inverse give me a shale. So this is all automated, and it just created these nice fascies logs all across our model, and it just saves us going through and manually interpreting them all or using a calculator statement. So I'm just visualizing them here. When we go actually into property modeling, there's a couple of things we can do to our data first. So here I'm actually checking for any stationarity in my data. So here we have a moving average along the bottom and then variance on the left. If you're not sure what anything is inside of Geology Designer, we have this little handy help tool. You can just click on the help tool and it will open up our manual, and it'll give you an exact kind of word breakdown of what all of our tools are. So here I'm just checking the moving average against the variance, and we want to see kind of randomness in our data. And then we can move forward with geostatistical tools like variograms and property modeling. So here you can see I have my porosity modeled, but you can see I have this kind of bivariate distribution, probably due to the fascies, different lithologies. You can actually remove trans here as well through the transformations, and you can also go in and manually kind of push and pull, force a normal distribution, add a function in here, do a custom min and max value. So now I've removed the trans, tNav is happy, and it will tell me about like the kind of stationarity in my data. And if I've got no stationarity or stationarity, and it will let me know if I can move forward with geostatistical tools. We're now creating a V-shale log by our gamma ray. So you can just put in a normalized gamma ray, and you can see here just from the workflow, there's a few different methods that I can use to kind of go forward with creating the V-shale. Again, I'm just plotting my V-shale log with my permeability, making sure I have this nice correlation between them, because I'm actually going to use one to co-create the other. So one will be reliant on the other. So I want to make sure that they have a nice correlation first, and also a correlation with the rock model, because we can use our rock model as a discrete property to then go and populate out our more continuous properties like permeability and like V-shale. So you can see we have our nice correlation there, this inverse correlation of V-shale and permeability. So I'm going to go forward and kind of co-create with them both and populate out my model. So I've used my zone property and also my fascies model to populate out my V shell. So we can see these nice bands of higher shale and lower shale volume. And I can also QC this against my initial well log data, which we always want to do, of course. So I'm just plotting my well log data on my cross section with this here, and then the same for permeability. So I can say, okay, the correlation coefficient is maybe negative 0.7, something like this for my permeability. And this just means that my V shell and my permeability properties are both tied together. Because we've created V shell and permeability, I'm just going to hand on some kind of fault scale analysis tools. So here we're calculating areas of adjacency, these kind of Allen diagrams, which allows you to kind of cross-check where your zones are touching each side of your fault. So we can do this for any discrete property. We can go in and if it's, zone, fascies, and we can see, okay, where is zone 4 touching zone 3, where is zone 5 touching zone 1, and we can really see the displacement across each of our faults and see which one of our zones and layers are speaking to each other. As I said, we can do this for any discrete property. So here I'm doing it with my fascies model. So I can see, okay, where's my channel, where's my floodplain and my floodplain? And of course, we can start filtering this data out as well. So in red, I've just got my floodplain touching floodplain, and in yellow, I have my channel touching my channel. So this allows you to see if there's going to be any cross connection between our faults or any kind of flow barriers as well. Now inside of Geology Designer, we can actually calculate our transmissibility multiplier, shale gauge ratio, displacement and thickness as well. So this is just what I'm doing here. I'm putting in my faults, putting in displacement thickness ratio, and then applying it. So I have this nice transmissibility multiplier as well. So this takes into account our permeability property, our V shale property, and then any kind of like displacement of our fault as well. So this is just the multiplier. We can also calculate shale gauge ratio, which takes into account these volumes, and then, yeah, I guess the displacement of the V shale past each other, so we can see how much kind of clay smear is happening within our faults, as well as the displacement. So again, you would normally expect the kind of lower displacement to the outer edges of the faults, and then the higher displacement in the middle. And we can start using some filtering tools to kind of filter out these values and really dissect our data. This is the shale gauge ratio as well. So this takes into account our perm and our V shale and the displacement of our fault. So this will vary fault to fault and zone to zone. And again, I'm just going in, filtering out some of my kind of like higher values. We can see where we have like our lowest shale gauge ratio, our lowest clay smear, and then our highest one as well. So now I'm just going to finish just by running it in a little loop. So this is called like a loop or a multivariate, and what we can do is we can add a number of different variables. So I'm adding a variable to the volume of shale. I'm also adding a variable to the oblique slip angle and also the displacement thickness ratio. So we're never going to be exactly sure of what these numbers should be. Of course, we can take an analog and then run it from this. But if we want to add some uncertainty and get some different variations from our faults, from our properties, we can do this super easily just in the workflow. So you can see I'm just panning through a few of my different shale gauge ratios, a few of my different multipliers, and you can see they're changing because it depends on what the shale volume was, what the displacement was, and then also what the kind of permeability that's relying on your shale gauge volume is as well. So yeah, you can see all my different displacements there. So I'm now going to hand back over to John, and he's going to take you through some fascies modelling.
Thank you, Jordan. So yeah, as Jordan mentioned, I'm just going to hop into some of our different algorithms we have in place for our discrete fascies modelling. Just obviously we'll cover a number of different scenarios that you may want to include in your projects. And with each new update, with each new development, we continually add to each of these algorithms to give you more sort of flexibility to control each of your discrete datas. So looking at the first option, we've got truncated Gaussian simulation. So if obviously within your depositional environment or within your geological concept, you want to control the fascies transition between one fascies to the other, we can honor this within our TGS simulation. So as you can see, I can modify it with my green arrows, moving the contacts between each fascies one by one. We also have this TGS trend within our data analysis hub, allowing us to actually manually click on some data points and move those fascies transitions in any sort of arbitrary direction that we please, that we choose. And this could be added back to our original TGS calculation as a trend. So as here you can see, once I've done this, you see we've got the original residual Gaussian field based on our variograms and well data, and I've added it to our deterministic trend data that we did our data analysis to output our overall TGS model. We've also got Gaussian simulation, so this has a different truncation strategy here, and essentially where we can assign both horizontal and vertical contact fascies transitions between one another. So as you can see here, I'm adding both a horizontal and a vertical transition. So in this case, my channel sand and my sandstone can only touch, whereas my sandstone can touch my fine sandstone in the bottom left, as well as my siltstone on the right. And as you can see here, when we go into our top right-hand side, looking at our model, we can see that the data honors this, and we can change our azimuth and run a number of different iterations to see each output. So we can see exactly what fascies touches the other. So this is a really good example of where you would want to honor your channel sand, but you can also do it for mineral deposits within the mining industry, and also looking at sort of your shore face transitions as well. We've also got object-based modeling, so we can model for channels, as you can see here, but also for levees, and with our updates, we're all looking at adding deltas and other objects as well. So we can affect things like our channel width, our thickness, our azimuth, the level of sinuosity with our channels, and the respective amplitude that comes with this channel as well. We can also auto-detect these parameters in, such as our sinuosity and its length, and we can also change the thickness too, so we can see each new iteration what changes with that. We also have hierarchical modeling, so looking at our original TGS model at the top left with our object channels at the bottom left, we can create an output where they're both combined together within a calculator statement. So we've got this combined hierarchical model where both our fascies models are being taken into account. We've got one fascies model, but what if we want more? So we can actually add within our workflows a multivariant, allowing us to reference a local variables table to output multiple iterations of one fascies. So looking at this, we can assign an algorithm type, in this case a Latin hypercube. You can use tornado plot, Monte Carlo. We can assign a number of variants we want, and with this, I'm adding new variables each time. So looking at my variogram parameters, I can also add my main, normal, vertical, a seed, and in this case as well, an azimuth too. So what you want to do is you want to anchor your calculation below your multivariant, and by doing this, it allows you to reference that local variables table that we created by right-clicking and adding our variables. So we can see that each new iteration that we output within this multivariant outputs a new discrete fascies model for us to sort of analyze. We can view this in a multi-window display, looking at each of our displays, both in 2D and in 3D, and we can synchronize our cameras with ease. It's also worth noting as well, we've got our, I mentioned we've got our PGS, our Gaussian, our truncated simulation, also our object-based modeling. We've got lots more, such as our SIS pixel-based algorithms, and also we've got our very own Amazonas algorithm as well. So this was developed by our own developers within our Rockflow Dynamics, and essentially it allows you to model discrete data and continuous data, whether you've got stationary data or non-stationary data. And if anyone wants to hear more about that, we can happily pass more information on towards the end of the session. So looking at our structural uncertainty as well. So we've managed to capture our first sort of uncertainty with our fascies model, looking at how we can create multivariants, these local variables table that allow us to be these variables to be referenced and output new iterations for each case that we can view in 3D. We can also look at structural uncertainty here. So within Geology Designer, we can assign uncertainty based on our horizons and also our faults, and we can do this a number of different ways. So looking at our point set data here, this is a hard data set where we've got our point set located at each wells. So this is a situated fixed mark. We can then go to creating a static uncertainty workflow where we can utilize Python codes, so we can utilize scripts. We can also, in this case, we're going to interpolate a horizon within our interwell space, and keeping those hard data markers at their points, and create error surfaces for both our top and our bottom horizons. So here we can see we've got a delta map here, looking at how our horizon flexes between this, or the surface flexes between each of our hard data points. We can assign a specific range we want our horizon to flex. So in this case, I've assigned it -2 to 2. So by viewing it in 2D, we can see within each of these error maps and each of the new iterations how these error maps change. and we can look at the normal distribution that we've achieved. So as I mentioned, we want -2 to 2. We can view this on a histogram to make sure that the data has been honored and that the flex that we've input into our calculation has also been honored. So that we can view this in 2D, and we can scroll through the different iterations, and as you can see with each new error surface map, how that flex changes. We can also view it in 3D as well, and this might give you a sort of better idea of what's going on. So those blue marker points, that's our hard data points attached to our wells. We can then see within the reinterpolated surface between that interwell space, we've got this flex from -2 to 2, which we then can integrate with our original horizon to use as a sort of an uncertainty horizon. So here we've created a multi-well fence attached to our markers, and we can see that our horizons that we've output, they actually come towards one another, towards our hard data points at our wells, but flex away by the given range that we've stated from -2 to 2. You can also attach a scalar to this as a variable that allows you to sort of flex it even further. So as I mentioned, we've got horizons, but we can also do it for faults as well. So we can shift our faults in both the X, Y, and Z direction. And just like we did with horizons, we can output these in 3D so we can see each new iteration and how it looks compared to the original. So within our cross section as well, we can see how the horizons flex with, and also how our faults appear as well within our space. So how this would look within our workflow, we create these @ symbols to define our variables, and we can put each of our new fault iterations as well as a new grid to be produced for each one. So we can see when we run our different grid iterations with those new faults, with those new horizon flexes, we can see how they change within 3D. So we can just see how the horizons or the grid itself actually shifts here and there. And we can view this in cross section again for a zone ID, and just to make sure that each of our new grids and properties that we output are sensible. So locating that AHM wand up there, we can see this is how we create our new insensitivity analysis study to capture those uncertainties. So we can run this based off a dynamic model, or in our case, we're going to be utilizing a table. So we referencing our objective functions such as our STOIP, our pore volumes, etc. We can assign a certain algorithm, so whether it's Latin hypercube, tornado plot, or Monte Carlo, as I mentioned, and assign the number of runs we want to output to see exactly how each of these variables have an effect with our given objective functions. So within this is our uncertainty engine. This is where we can capture each of our variables and see how they affect our project. So within our project info itself, we can see each case and how one variable, each value's variable, each variable's value, sorry, for each case. We can also see the calculation time it's taken for each of our iterations to run. And within this page here, looking at our objective functions and results, we can see exactly how our data is displayed. So looking at the bottom right, we've got our table. We can sort between our cases for specific objective functions, looking at what cases have the highest values. Within our crossplot data, we can see exactly for, in this case, our geometric volume, if our given fault has any trends attached to it. We can also view our Pareto charts, or if you ran a tornado algorithm, you can view your tornado diagram as well. And we can quite quickly see when we sort our data what variables have the greatest effect on our overall objective function values. And looking at our CDF curves as well, we can look at our P90, P50, and P10 cases. You can also add further quantiles to this as well. So if you want to add P75, it's a very quick process, just a couple of clicks to add them in. And a really nice feature as well that we have is when you zoom into your CDF curve, looking at a specific point. In this case, if you zoomed into your P50 and selected that individual data point, it would highlight in your left-hand side, which we can see here, to that specific case that's been used. And then you can actually right-click and select variables from this case back to workflow. So it essentially takes if we selected our P50 case, it would take these values for this, for each of our variables, and reference it back to our original base workflow, so we can then run that workflow and output a base model. So this is a very powerful tool. Allows us to quickly see not only obviously looking at uncertainty overall, we can output multivariates to allow us to see how each of these models look in real space in 3D, for example, or we can run it through our AHM uncertainty engine, allowing us to see exactly with hundreds of cases, thousands of cases, exactly sort of the range and the effect that each of our variables are having on our objective functions. So we've got a lot of flexibility through our workflows to capture this. And even better, obviously, once we've captured our uncertainty from the static side, we can simply pass it over to a reservoir engineer using the exact same workflow. They can add in their dynamic variables and pass it back into our AHM uncertainty engine here to run forecasts. So it allows this constant collaboration between one user and the next, between your different departments, and it's a very powerful tool. So hopefully, going through all of this, you managed to capture a lot of the different functionalities that we have within our static modeling solutions, how we can use a number of different functionalities, building up our static models to really transform your project, and looking at how our workflows are a very powerful tool in doing this. But thank you for listening, everyone. If there's any questions within the chat, we'll try and answer some for our remaining time. And if not, we'll always get back to you after the session to follow up. And if you're not already aware, we've got another webinar session after this. It's this Thursday. And it'll be looking at probabilistic methods for assessing our CO2 migration pathways. And this will be run by our colleagues Serkan and Marcus. But yes, hopefully you took something away from today's session, and I'll pass back to Joanne and we can conclude with some questions. Well, thank you, everyone.
Thanks, John, and thank you, Jordan. Yeah, that was a very comprehensive presentation and a lot of information fitted into a short time, so well done, guys. And we'll have a look. We got a few questions for you, so 1 second. Can you include seismic interpretation, such as seismic attributes, into your reservoir model?
Yes, so for seismic, yes, we definitely can do this. So we can bring in like our SegY volumes, our ZGY volumes. We can calculate attributes here, or of course we can just import attributes from a second party software. We can then upscale this to our model or kind of resample it into our grid, and then use this as either like a trend or something like cold kriging, and then yes, use this in our model as well.
Okay, thank you. And can we incorporate fractures such as DFN?
Yeah, we absolutely can. So DFNs are actually treated as individual objects within Geology Designer. So if you're ever in your project, you'll find DFN just listed under faults. And we can create DFNs based off of, you can create DFNs off faults, for example. You can assign the number of sides, number of fractures you want per fault. And within these DFNs as well, you can then, with them, output attributes for each one. So your aperture, for example, and your respective permeability comes with this, and they can be resampled very quickly back into the original grid as well. So you've got your DFN related permeability as well as sampled into your original permeability models.
Thank you. We'll just do a couple more questions. We do have quite a lot in the chat, so we probably won't have time to get through them all, but we'll definitely make sure that we follow up with you. So let's do 2 more. How easy is it to take your models into simulation and pick and choose your models for forecasting?
So yeah, with tNav, I don't know, I mean, you probably didn't see from the video, but at the top, there is literally a button that says like take through to simulation. So within Geology Designer or Model Designer, they're the kind of same, they're the same interface. We can set up all like our fluid properties, set them all up inside this interface, and then just click run simulation. So you can actually run your dynamic model straight from Geology Designer. And the way it works with like the reservoir engineers and the geologists is we would both work off the same workflow. So I would set up my static modeling workflow, like property modeling, creating my model, running any volumetrics and uncertainty, and then I would hand it to the reservoir engineer. They would be able to add their kind of dynamic properties at the bottom if they have any calculator statements or any uncertainty that they want to add. You can just add this onto the bottom of the workflow, and then we can just push this one full kind of loop workflow into simulation or into assisted history matching.
Thanks, Jordan. Let's do one last question. Do we have any petrophysics tools to help edit our logs and calculate V-shale, porosity, saturation, permeability?
Yeah, so I mean, obviously, Jordan, you probably covered that with some of your videos within there, but we have we're constantly adding more petrophysical sort of functionality with each new update. But at the moment, within our sort of for your logs, you'll find when you go to your calculations, we've got a dedicated petrophysics tab. So when you click down that, you can find sort of your water saturation sim and do equations. You can find your porosity, density, and permeability equations within there. So obviously previously you would have had to like calculator statements based off doing it manually via these equations, but now we've got the ability that you can just click on the equation that you desire and output from there. And yeah, we've got volume shale equations available. So looking at your Lanarov, Clavier, we've got a number of different variations that you can choose from.
I think we're just a way to release our newest release actually. So we have 4 main releases a year and then some kind of patch releases in between them. But just looking at the release notes from our newest release, I can see that they added a whole heap of new like geomechanical equations in 24.1. So yeah, it was definitely something that we're really pushing, like geomechanics, and then also kind of more petrophysical calculations as well.
Thank you. Okay, let's fit in one more question. Does your seismic function include depth conversion?
Yes.
Yeah.
So I was just going to say, so we previously with a few versions, like maybe as of last year, you would have had to import sort of a velocity model from an external platform, but we can now create velocity models. So using your horizons at time and your markers at depth, we can create basic velocity models, and then from there allow you to carry out your domain conversions. So you can also use your sort of your check shot data and your TDR logs as well to visualize that in 3D and switch between your time and depth. So yeah, we've got functionalities in place that allow us to do that.
Okay, thanks so much. So as John mentioned, the next webinar, which is the last one in this series, is on Thursday, and that's probabilistic method for assessing CO2 migration pathways. And if you do happen to be joining us from Norway, we have a technical talk on in Stavanger today and in Oslo on Thursday, so you can drop us a message if you'd like to come along. We'll share some company updates and technology updates from RFD, and Jordan will be presenting her fault seal analysis workflow as well. So if you are around, then you should definitely come along to that. And if not, we hope to see you at the next webinar on Thursday. Thank you everyone for joining, and thank you Jordan and John for the great presentation as well.
Thanks for joining, guys.
Thank you for joining, guys.